Hey, it's Spyro at BindRecord.org, and I'm joined by you.
Yes.
Yes, Keithius.
Yes.
And this is another one of his computational historians videos.
Jesus Christ, it's not that difficult to get right.
I'm not trying to get it right, I'm just trying to change it every time. So,
it's computation history, not historical
computation.
computerist or whatever the hell it was this time.
Okay, so last time it was Ada Lovelace. This time
Yep.
it's Claude Shannon. And
Yes.
he, much like Ada Lovelace, he has a little title, and it's the father of information theory.
Yes.
What does that mean?
Well, I wasn't going to start there, but...
No, fine. Start where you want to start.
Okay, well, I'll start there because, yes. Okay, so he basically came up with what we now call information theory, which I'm going to get to in detail later on, so that's like the really brief answer to your question.
That's what I said. That's not really an answer to the question.
No, it's not. But you can wait, because in order to explain what information theory is, it's kind of complex, so we'll come to it in a bit.
Okay, so what are you going to tell us about Claude Elwood Shannon?
Okay, I'm going to give you a quick, brief history about him.
Yay!
Yeah, okay, cool. All right, so he was born in Michigan in 1916, and he went to university in Michigan.
Which university?
The University of Michigan.
Okay.
Strangely enough, at the age of 16, which
That's
is pretty young. But it gets more impressive. He graduated 4 years later with not 1 degree, but 2 degrees in electrical engineering and mathematics.
Huh.
So he not only did he go to university at the age of 16, it's like 2 degrees at the same time.
Yeah.
So the guy is pretty smart. I think that's kind of an understatement.
Is that the only university he went to?
No. That was a really weird no. But no, it's not. He went to MIT after that and did a master's degree, and then he went to MIT again, or rather stayed at MIT and did a doctorate as well.
As you do.
Yeah.
That's what I'd do if I was at MIT. I wouldn't leave.
Well, he did actually leave, and he went to work at Bell Labs, which was one of the kind of first major telephone companies in the US. And after that, in 1956, he went to work at MIT and taught there, which is quite cool.
Was he teaching mathematics or engineering?
Bit of both, I think.
Okay.
Yeah, and he was kind of like known as being a bit of an unusual person. He did things like, he liked juggling and unicycling, and he played chess and invented lots of machines, including one that has gotten kind of quite popular again lately called the Ultimate Machine, which is kind of a joking title. It has one function, and that's to turn itself back off. So it's basically this box with a switch on the side. You press the switch, the box opens up, a lever comes out, presses the switch, turn it off, back off again, and the lever goes back in.
I've seen those.
How cool are they?
Yeah, no, I remember that. It's a button, and the thing pops out, and it turns the button back off. Yeah, no,
Yep.
I saw that, and I didn't know that was made by him.
Yeah,
that's pretty cool.
So that was pretty awesome. But that isn't like the best thing he did, but it's pretty
There
close.
are things better than that. Wow.
Yeah. All right. So I'll give you a quick summary of his kind of major works. He published loads of papers, a huge number of them, on all sorts of topics. But his 2 sort of most influential ones were his master's thesis and a paper he released then in 1948 as well. His master's thesis was called A Symbolic Analysis of Relay and Switching Circuits. And it was quite revolutionary because he applied Boolean logic, as in true or false, which in other words is binary, to relays and switching circuits used in automated telephone exchanges at the time. So it was basically a way to model how those systems work, and sort of it was the foundation of the work he went on to do later on, which was pretty much summed up quite nicely in his second paper that I'm going to talk about, which is called A Mathematical Theory of Communication. And he published that in 1948, and that's basically what information theory, that mysterious subject, is based on. So, do you want to know what information theory is?
I do. What is information theory?
Well asked. So it's a theory about storing and communicating data. And in the paper, Mathematical Theory of Communication, Shannon basically worked out a way of defining information and then how you can measure it and how you can compress it and so on. And that kind of leads on to the question, what is information anyway? And it's kind of difficult to measure, but one of the key sort of factors...
Just stop you there. Isn't that just data with a meaning or with purpose?
Not really, kind of. It gets way more complicated than that, because we're talking about like a specific case when it comes to communication. So it's kind of like you could talk about information being data with meaning, but there's more to it than that. And we don't really care about the meaning of information, because how you communicate information electronically or store it, the meaning doesn't matter. So it's like how do you measure it, which is the sort of tricky part. And the answer is entropy.
It's always entropy.
Oh, it's always entropy. But it's used in perhaps a slightly different way, but it's essentially the same thing as in thermodynamics. And as far as information is concerned, entropy is it's kind of difficult to explain, but basically it's a measure of surprise. So
okay.
I'll explain this with a couple of examples. So if I were to say to you, today is, what are you going to say next?
Is this to do with an objective or a subjective way of looking at things? Because I've done a few psychological experiments that involve that sort of question. Or is it nothing to do with that at all?
Nothing to do with that at all.
Okay, so today...
It's purely information, but we don't care about the meaning.
Okay, today is, and you want me to answer that?
Yeah.
This
word.
Okay, Wednesday.
Right, okay. So if we say today is Wednesday, so if you think about that sentence, because we're specifying today is, there's only a set number of words that can follow, which means that we have less surprise. So there's less entropy, because there's a smaller set of words that might come next. So, for example, having today is Wednesday is less likely than today is panda.
Okay, well, for another test, let's have a look. Today. Let's see what my phone thinks the next word is. Today is, and the options are a, the, or my. Because it's thinking about a sentence. And it's also thinking about what words I have used most often after the word is.
However, you can still think of it, though, as the same thing, because it's only a small subset of words that are likely to come next, and there's a much larger subset of words that are unlikely to come next.
It's also got going, not, an, it, that, and to.
Well, if I type today is into Google, and its recommendations are today is the day lyrics, and today is National What Day, and that last one doesn't even make grammatical sense, but whatever.
I've got today is a good day to die.
Hard. So anyway, continuing on. So why does this matter when it comes to information is the kind of next question, and it's all about how do we communicate reliably. So if you think about natural language, there's a huge amount of redundancy. Shannon did some work on this, and he reckoned that upwards of 50% of the English language, when communicating, is actually just redundant words to convey meaning. So you could use a lot more words to say something than you actually need to. Strictly speaking, if you were to sort of break down the English language into like a mathematical formula, for instance.
Of course.
So there's a lot of redundancy in there. And going to go off on a bit of a tangent. There's this book that I read kind of as part of my research for this called The Information History, A Theory of Flood by an author called James Gleick. And he talks about in Africa, there is what they call talking drums, and it's how tribes communicate with each other over long distances. They have these huge drums and they hit them, and basically each sort of different type of sound has a different meaning, but they're really verbose in what they play. So rather than just saying a man in a hat is coming to see you, they'd have something like a man in the hat is going from a long distance away towards you from this direction at this time or whatever. So they add a lot more redundancy in there, but they don't always increase the meaning, but it's basically to make it so even if some of the bits of the message are missing, or even if some of the information is missing, you can still work out the meaning, which applies to information as an abstract concept as well.
That sounds very much like a more recent way of information being sent, with sort of checksums and whatnot.
Exactly, which is what this is all going to lead up to as an example. So this was kind of like all basically covered off in the paper I mentioned, A Mathematical Theory of Communication, which a short while afterwards was actually sort of padded out and released, and basically this popularized it in a book credited to Shannon and a guy called Warren Weaver. And this guy, Warren Weaver, basically took Shannon's paper and sort of expanded on it and made it more publicly accessible, which in turn made it more interesting to people outside of the fields of sort of electrical engineering and telecommunications and so on. And there's a lot of it kind of changed the way people like geneticists looked at the human body and, well, basically all times of life, and how everything is basically transfer of information. So DNA is just information, and there's a large amount of redundancy in there as well. So it quite revolutionized quite a few fields at the time, because it's sort of like a new way of looking at it, rather than a specific, say, cell doing something or whatever. It's the kind of the concepts behind it.
Okay.
So that leads on to sort of the next part, which is how do you deal with things like noise and so on, and encoding and decoding information, because we're still talking about sort of redundancy and reliability of transmissions. It's like, as you mentioned about checksums, we want to make sure that we can communicate information reliably. Even though we don't care about the meaning of it, we want it to get there, either fully intact or as intact as possible. So this goes into what information theory is used for. And these kind of concepts of how do you encode information, or how do you transmit it reliably, or even store it reliably, and you could argue as well, it's all basically down to like the theoretical underpinnings and the model that's brought in information theory. So things like how do you cope with a noise source, and as you said, right, with checksums, it's basically you can take the data and say, okay, so if I've converted my data to binary, all the digits should add up to this value. So if your checksum becomes corrupted or your information becomes corrupted, there's a mismatch, you can tell that it's not right. And this kind of also translates into, well, the main part it translates into these days is how we communicate through like telephone networks, the internet, and mobile phones. The one with checksums is things like packet data and so on. Telephone networks, traditionally they operated on circuits, but these days they get them digital as well, so it's the same concept. But mobile phones is an especially interesting one because the sheer amount of noise involved. So because you've got a huge distance between your mobile phone and the mast, it's like how do you create a reliable way of, or reliable channel of communication between those 2 points before it goes onto the regular wired network? And by using sort of the theories and the models that Shannon came up with, you can come up with ways to actually reliably transmit that data and retransmit bits that are missing and so on, or drop data if it's not needed. It seems like you'll not notice a lot of phones these days, if you stop talking and the line's clear, then it goes to silence. So basically it detects sort of the level of noise and then just drops any of that sort of data. The other one is compression, which is things like MP3s, JPEGs, PNG images and so on. And all that sort of compression is basically how you can represent the same amount of information in a smaller amount of space.
Isn't that to do with fractals at times?
Don't know.
I remember reading something, it was you use a very basic, so say you have 4 pixels arranged 2 by 2, 3 of them white, 1 of them black. You can just rearrange that one image several different times at different rotations to create a much larger image. So you're actually using one image several times to create a larger image.
Yeah, I mean, you could create fractals that way, which is like, that's kind of another encoding mechanism.
Yeah.
The way that it's normally done, though, is that you'd have, say, if you have those in a line, because basically you've got a stream of information, you, instead of saying white pixel, white pixel, white pixel, black pixel, you say 3 white pixels, 1 black pixel.
Yeah.
And you basically just take that encoder, and that's shorter, which is how most compression algorithms tend to work these days. There are other ways of doing it which are quite clever, that does it, say, across a longer file. So rather than just looking at contiguous matching information, it'll look at bits in other parts of the file as well, and perhaps put pointers to where it should be in that file. So you can kind of, in a way, deduplicate instances of white down to like a small bit of data saying that we've got at location 0, 4 bits, at location 20, 3 bits, and so on. But yeah, essentially, same kind of idea.
Okay.
So a few other works that Shannon did as well on top of information theory. And one of them was... Sorry.
So is it a rocket-powered flying disc and a motorized pogo stick?
I don't have those on my list, but they're
what about a
flame-throwing
trumpet?
We'll get to those shortly.
Okay.
These are still like his concepts and ideas at the minute. And one of them is what's called Shannon's maxim, which basically states the enemy knows the system. And this is a really important concept in security, where you should design a system so that even if your attacker knows how the system is designed, and this is even more so in cryptography as well, they should still not be able to compromise that system. So if they know basically what encryption algorithm you're using, they shouldn't be able to decrypt your text with just that information. They should need some other information to do that. And the same thing goes for a system. Just because they know like your network layout, they shouldn't be able to compromise it from that.
Right.
So that's quite an important kind of concept. There is like a reverse concept called security through obscurity, which is a bit of a joke. It's basically if someone doesn't know something, how can they use that information to leverage it against you? So it's like knowing, say, the IP addresses of servers or a network layout, for example. But that's just security through obscurity. That's not real security. So basically, Shannon's maxim is kind of like the antithesis of that and an argument against it. Another thing that is quite interesting as well, I would say we, but probably just me, I'm quite a big fan of Alan Turing. And in 1943, Alan Turing and Claude Shannon actually met for a few months, and they used to like have lunch or something like that together. And unknown to each other, both working on the same problem at the same time, but because it's highly classified, they didn't know about it. And that problem was the basically how do you encrypt speech? Because during World War II, Churchill and was it Roosevelt?
Woodrow Wilson. No, he was World War One. So yeah, Roosevelt.
Yeah, Churchill and Roosevelt wanted basically to talk on the phone, but obviously wartime, and the Nazis would be listening in. So this problem was sort of put out to a few different people. One of them was Bell Labs, where Shannon worked, and the other one was Turing when he was at Bletchley Park. So it's like, how can they encrypt speech? And they did come up with a way of it, which is... Do you want me to go into that?
Yeah, go on.
It's quite clever. It's basically they take... they create a disk, and think of it as an LP, and they'd have all these indents in it. And they create a matching disk, so you had these two disks exactly the same. And what they would do is they would play these disks exactly at the same time on both ends. And then what you could do was you mix in the person's voice with that, the noise coming from all these indents in this disk, and at the other end you subtract it again. So basically it's like a one-time pad, but for voice, which is pretty damn clever.
That is pretty good.
So that's what they're both working on at the same time, but they never actually discussed it with each other because they weren't allowed to, and they didn't know the other one was working on it. But that was quite interesting as well. But here's onto the next bit, though, is what I've called the fun bits, which are things like you were talking about, like flame-throwing trumpets. He came up with a theory for juggling. He was quite an avid unicyclist, and apparently he used to go into Bell Labs and ride around on his unicycle, just for fun.
Say, I want to know about Shannon's mouse. Do you know anything about that?
Yep. Okay, so I was kind of hoping you'd ask about that one. So what he did was he designed this electrical mouse, and it was hooked up to a whole bunch of relays, and it was given a maze that could be reorganized. And what the mouse would do is once you set it in motion, it would basically go through the maze and figure out a path through it, so it would keep trying different iterations until it got to the end. If you bit the mouse up and put it back at the start, as long as you didn't reconfigure the maze, it would do the same thing again. But if you reconfigured the maze, then it would relearn it and do that once again.
The mouse was named Theseus, wasn't it?
It was, after some Greek god. I can't remember who.
It was Theseus, who is the former king of Athens and son of Poseidon.
There we go. But this mouse was, well, pretty damn cool. and it was actually basically an early version of AI, really, artificial intelligence, because it learnt the route through the maze. There's another interesting tie into Turing here, although I don't know whether Turing and Shannon ever talked about this. There's no sort of record of that, but Turing is also quite well known for a paper he did called Can Machines Think, in which he's basically talking about, well, whether machines can think, so artificial intelligence.
Yeah.
Another quite cool thing that Shannon did was he built a chess computer. Apparently it was probably about novice level. I mean, it's nothing like compared to sort of today's computers, but this was the 1940s. So at the time, it was quite a phenomenal achievement, and he sort of quite a lot was learnt about the game chess from that, in that it's very difficult to compute like so many moves ahead, and it's kind of more based on like probability. I mean, there's a high level of intuition when it comes to playing chess. You can't calculate every probability because you get into things like NP-complete problems where you can't compute it in non-deterministic polynomial time.
There's too many variables.
Basically, yeah, it's infeasible. It's the traveling salesman problem.
That's where I was going to go with it.
Yeah. And one other really cool thing that Shannon did was he developed a method of card counting in blackjack. And you hear about the team from MIT who went to Vegas. I think it was sometime like the late 90s, early 2000s maybe. And they used card counting to make a load of money. There was a film made out of it with Kevin Spacey called 21.
Yeah, that film didn't really go about card counting in the correct way, but yeah.
Well, basically, what the actual real people who did that did, they based their method of card counting on Shannon's method of card counting.
Okay.
So
using game theory then?
Essentially, yeah. I mean, that's one of the things that's sort of quite important about information theory, is that it's had quite a big influence on game theory, and it's kind of like, because game theory kind of boils down to information anyway, it's a similar sort of thing, which is quite cool. I think you'll agree.
Oh, definitely.
So I think we're kind of wrapping this up. I want to mention a couple of sources, which I've already mentioned, but I'll mention them again, and they're going in the notes underneath this video.
Cool.
One of them was the book called The Information History of Theory of Flood by James Gleick. It's a great read. It's the one where I got the anecdote about African talking drums from, and a lot of information about Claude Shannon. It basically talks about sort of information, both information theory and kind of information, how it's evolved over time. And there's a lot of really interesting stuff at the start about natural language as well. So that's pretty good, and it does a great job of explaining what's a really complex subject. And the other one is The Mathematical Theory of Communication, which Warren Weaver changed the A mathematical theory into the mathematical theory, so a bit of a change there. And that's also a really good book, and it goes into, well, it's basically Shannon's paper. And I recommend reading that if you have an interest in information theory. To kind of wrap up, Shannon sadly passed away on 24th of Feb in 2001, but the impact he had is quite phenomenal. We wouldn't have the information society we're in today, or at least not yet, if it hadn't been for Shannon. That's kind of like how much of an impact information theory had on just that area alone, but then there's the kind of impact on psychology and genetics and all sorts of other fields. And that's it. Any other questions?
No, I think you covered all the things I want to go from. Just want to say that he got quite a few notable awards.
Oh, yeah, he collected awards like you wouldn't believe.
Yeah, he's got the the IEE Medal of Honor. I say EEE, there's 3 E's in that thing.
IEEE, yeah.
Yeah, the National Medal of Science, the Harvey Prize, the Koto Prize, and the National Inventors Hall of Fame, which he got after he died in 2004.
There's actually, I watched something a while back, and there's a prize named after Shannon as well, in the field of information theory.
Oh, yeah?
I can't remember the knife for me what it's called. It's just you mentioning it now has briefly reminded me. But oh, here we go, Claude Shannon Award, and it's awarded by the IEEE Information Theory Society to honour Claude Shannon, And it's the most prestigious prize in information theory, covering technical contributions at the intersection of mathematics, communication engineering, and theoretical computer science. And the first winner of the Claude Shannon Award was Claude Shannon in 1972.
Well, if you're going to win an award, make sure it's the one that's named after you. That's what I say.
But the thing that was quite impressive is that the guy was very modest. He was known for being sort of a kind of quieter sort of person. And a lot of things like his huge impact with his paper on a mathematical theory of communication, that wasn't that widely known other than people in the kind of field until Warren Weaver sort of adapted it into the mathematical theory of communication, as in the book, and made it sort of more publicly available and made people more aware of it. So he was quite a modest man as well.
Which is always good.
It is. So, thank you, Claude Shannon, and happy something's birthday.
Oh, well, he was 84 when he died, so 94...
He would be 97.
97, yeah.
Yeah. So, happy 97th birthday, Claude Shannon.
So, yeah, so if you enjoyed this video, go back and watch our Ada Lovelace one as well, because that one was pretty good.
Oh, yeah, I quite liked it. And so obviously it's a weekly series, a week occurs about 4 months apart.
Oh yeah, I did say it was weekly series. But you have got more of these planned for the year, don't you?
I've got some names written down, but I've not researched any of them. This was kind of like the biggest one that I've researched. I mean, it involved reading like 2 books and watching lots of things and reading a lot more. So I don't know whether future ones will be quite so in-depth.
Yeah, so we don't skimp out on the sources. We make Dave read a load of books.
Or rather, Dave reads a load of books and decides to blabber on about them for half an hour.
Yeah, all that. But yeah, so we want to hear what you think about this guy. Did we miss anything? We may have missed some stuff. He might have done something awesome we don't know about. We want to see it in the comments below.
We definitely did miss some stuff out. Because
we could have been. You could have been talking for hours if you allow you to do that. I'm sure there's loads of things about Boolean algebra you want to talk about, but don't worry about it.
There is so much more that I want to talk about, but that's it for this time.
Yeah, but yeah, so like, subscribe, and all that jizz.
And thank you for listening.
Yeah, that too.
Cheers.